Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video we'll continue to learn more about pandas. In this video now we'll look at the intuition behind what is exponential weighted mean, what is exponential weighted standard deviation and variance. So there won't be any coding. I'm just going to walk you through a couple of pictures and we'll go through some mathematics at the end of this video. So to calculate the exponential weighted values such as mean, variance or standard deviation, we need to use a value of alpha, and alpha is calculated as shown in this formula, which is 2 divided by 1 plus span, and span is the span. Let's say if you have days, if you are looking at data over a couple of days, then you can say that the day span would be 5 days span or 10 days span or 20 days span, or which you want to uh, uh, get the weights. So based on that we calculate the alpha, and as you can see in this plot, as the value of alpha is increasing, the value of span decreases, or vice versa. As span increases, the value of alpha it decreases. And span, the alpha always lies between 0 and 1, and span has to be greater than or equal to 1. Similar to span, there is another quantity, center of mass, from which we can calculate alpha. And similar to span, here in the orange curve we can see that again, as the value of center of mass increases, the value of alpha decreases, or vice versa. As alpha increases, the value for center of mass decreases. Finally, we have this quantity called half-life, which is the time it takes for a quantity to reduce to half. And as you can see, when we calculate alpha from that, they are also inversely related. So as the alpha is increasing, as shown here in the green curve, the value for half-life also is decreasing. So what does span actually do? Well, let's look at another example. Here we have a data set. It has around 10,000 points. Now remember, span can be used to calculate alpha, which can be used to calculate weights, and weights is what defines or decides the importance of each data point. Now if we calculate the weights with three different spans, say 3, 30 and 300, we can see here that as the iterations increase and we are going down the data set, first we look at just 2 points, and then we have 1 point, 2 points, 3 points, and so on and so forth. If the span is set to a lower number such as 3, you can see that the importance of the older points diminishes very quickly. And here we can see that this in just 1 2 3 4 5 6 iterations, this has gone to 0.03. However, if you have a higher span, for example 300, then even at that iteration the importance of that data point is still 0.96. So there is much higher weight assigned to the older data points as well, farther back in time. So when you look at the plots in few next slides, will show you that when you try to fit the data set with the exponential moving average that is a higher span, the curve therefore would be much flatter, because you are giving more importance to not only the new points but also the older points that are in the past. Whereas if you have a smaller span such as 3, then you give more importance to only the newer points and very less importance to the older points. And that's what that does is a lower span therefore keeps the noise, and it does not smoothen the curve as much as the span of 300 would do. Additionally, here you can also look at another point, which is as we go to the next row, when the weights are calculated, the weights from the previous row are used. So for example, 1 is carried over, then 1.5, 1 and 0.5 are carried over, then all these three data points are carried over in the next iteration, and all these four weights are then carried over to the next iteration. So that's how the progression of weights happens when we are using exponential weighting. Now coming back to this figure, and when we plot the alpha at pointed, we see that they are very close to the original data points. We increase the alpha, the values are much more flatter, the curve is much more flatter, and we can see that with this magenta colored dotted line. Now what happens if we use the span as a way to uh, add weights to the function? When we use span again, for let's say 2 days, if you use 2 value of 2, then it's much smaller window, and therefore the values are much closer to the actual raw data, and there is still significant noise. Now if you change that to 20 days, so now you are spreading the weights over a large number of days, and therefore the as seen here in the yellow line, we can see that the curve flattens out and becomes much more smoother as compared to the original data. Finally, looking at half-life, if we have half-life of set at 2, then again there is much noise in the data as shown here in the blue, and if we change that to 20 days, then as shown here in the cyan curve, we can see that the curve is much more smoother as compared to the 2 days. And before we end this, I just want to show that if you use the center of mass, again the similar analogy applies. With less number of days, we still have some noise in here, but if you increase the number of days to 20, then the curve that you see is much smoother. And this is the final plot that shows the combinations of the window sizes and the values of span, half-life, center of mass, and alpha. And you can see that the larger the values, the more smoother the plots are, and the lesser the noise is in those plots. Now let's look at how we can calculate these values, or what goes on in the background to calculate these. Here we have a data set where we have the column Z, and it has these 5 values: 10, 20, 12, 14, 15, and we are going to attempt to calculate the exponential weighted mean in this case, variance, and also standard deviation. So as you can see in this figure, we are going to initially consider just 2 data points. We'll set the span to 3, and then based on that we can calculate the value of alpha, which is 2 divided by 1 plus span, and we get that value to be 0.5. We for now we won't use other two methods because we already have the value of alpha from span. Next, what we need to do is calculate the weights for these 2 data points, and to do that we go in a reverse order. So the most current data point will set it to 1, and then the point before it will set it to 1 minus a. A is alpha, so 1 minus 0.5, and so we have value of 0.5, which is the weight for 10. Now you're probably imagining what happens if we have 3 data points. So if we have 3 data points such as here 10, 20, and 12, then we are going to again go in the reverse order. Most current data point is 12, we assign it value of 1. Then going back, for 20 we have 1 minus alpha, so that comes out to 0.5. And then for 10 we are going to assign 1 minus alpha to the power 2. Okay, so we are going to increase the powers now. And similarly, if we go to the next step where we have 4 data points, we add 14 here. Then again we assign 1 value to the most current data point, which is 1, and then 1 minus a for 12, 1 minus a square for 20, 1 minus a cube for 10. And so the weights would be 1.5, 0.25, and 1.25. as you can see, we still have the last data point, except that we have now reduced its weight to just 0.125, and we give higher weight to the most current data points such as 14 and 12. As a next step, what we want to do then is for the first two data points that we had earlier, we got the weights, we can calculate the sum. So sum would be 1 plus 0.5, 1.5, and then we can get the square of that. So that would be square of 1.5, which is 2.25. And next we can go ahead and multiply the weights with the values that we have in column Z. So 0.5 into 10 is 5, and 1 into 20 is 20. Then we sum these two, so we get 25. Moving on, we can go ahead and square these values as well. So square the weights. So 0.5 becomes 0.25, 1 stays 1, and then we take a sum of that. So sum of 1 plus 0.25, we have 1.25, and this can be used to calculate the exponential moving mean or exponential weighted mean. So here the formula is sum of WZ, so which is in red. We divide that by sum of W, which is here in blue. So 25 divided by 1.5, we get 16.667. So that's the exponential weighted mean, which would come next to 20. So in 10 would be NN, so we start at 20. So this value here for that exponential weighted mean would be 16.667. Now we can also go ahead and calculate the bias. If you remember from the descriptive statistics video, bias is we use that for deciding if it's a sample or population data that we are using, and if you need unbiased data, then the Pandas function default is unbiased, and because it's set to false, and to calculate it values for bias that is false, we need to use this formula where we use sum W square, which is in red, which is this one, divided by a difference between this sum and the sum here, which is sum of squares of W, which is in blue, and thus we get this value of 2.25, and we are going to use this value next to calculate the exponential weighted variance or exponential moving variance. And before we do that, we need to compute the values in this last column, which is W into Z minus EWMA, which is the exponential weighted mean, and square of that. So to get that, we have, for example, for the first row, we have 0.5 as the weight, which we calculated here. Then the value is 10, which is in column Z, and then the exponential weighted mean we have calculated earlier, which is 16.667. So we add that here, have that here, and then take the difference, get a square of that, and multiply it by 0.5, you get 22.224. And similarly, we do the same calculations for this next row, and then sum these up, and we get a total of 33.33. So we substitute that in this formula right here, and now we have 2.25 into 33.33 divided by sum of W, which is in green, so 1.5, and thus we get exponential moving variance or exponential weighted variance of 50 for this row, which is 20. And based on that variance, we can also go ahead and calculate exponential weighted standard deviation, which is just square root of variance. So we take a square root of 50, and that's how we get the variance of 7.07. That was it for this video. I hope in this video you got an intuition of how the exponential weighted mean works, and what are the advantages of using exponential weighted mean in certain situations. where you do not want to lose any data points. You still want to keep them, but just reduce the weight of those data points on those data points while calculating values such as mean, variance, or standard deviation. In next video we'll continue on this topic and look at its implementation in Python. Please like, share, and subscribe. It helps me stay motivated to create more interesting content for you all. Thank you.